coming back to, okay, so let me come back to our motivation for coming back to this problem is due to the experimental developments, the ability of people to actually measure directly the dynamical density correlation function for electrons in certain number of materials, which was not possible years ago when we field was more. And so we decided to, of course, it's a hard problem with this work done with a really brilliant graduate student, Matthew O'Brien, who this time of the year he migrates back home to Australia, where it's a little warmer. So not unlikely that. So he's in Australia. Okay, so let me give you a lightning review of these many things that I know, and I have by no means exhaustive. So what's the CW is the modulation, it's a spontaneous modulation of the local charge density. And we write that as we take the charge density. There will be some average density, which may also be slowly varying. And then the modulated part stays. So in this case, I'm going for simplicity, assume that it's unidirectional with the wave vector here. Okay, of course, in materials, the three-way, then the many charge density was a very low, that's for the moment. And the quantity of QR, which is slowly varying, in other words, the rapidly varying part in this decomposition, which is exponential, the slowly varying part plays a role for a normal parameter, and because this is the Fourier transform of real density, this is a complex field which has an amplitude effect. Okay. So that's basically how the fields are actually written down. But because this is actually a modulation of the charge density, it couples linearly to the solver in the forms of charge field. So in fact, the solver couples to this problem as a random field. Yes. So it's a prototypical random field problem. It's not like the random field Ising model. The memory of the work for myself to pronounce it correctly, so Ising not Ising. It's not on the missing mode because the symmetry here is going to be continuous. That's why you have a complex field which has an amplitude and a phase. That's that example that here out on the board. And what matters there is are the phase fluctuation to the keyboard and the phase. There is the program started by many people. It was sparked the work by Joini and Shanma in 1975 and effort of Matthew Darkin. Probably at the same time, but by the time this was published in a translated form, there was a 2-year delay, but there was simultaneous. So they showed that any dimension below 4, there is no true range order, no matter how few impurities you will remove, there is no true range order person.
So this incommensuration is like the Q vector with respect to
It's incommensurate.
With respect to the lattice?
With respect to the line. Because a continuous symmetry. So you can slide the symmetry. Now, so then there's usually there are threshold fields that mean giving the dynamics, which is the classical dynamics, which is interesting, and much of the work is done. In this context, in the context of the CW, papers by John Carvey and Stephen Meston in 1982, and at the same time by the University of Benny Hauptmann. This problem actually to prove how the KT transition is displayed by this local coupling to the random impurities is not actually simple problem, and I don't think these papers actually gave the final solution. The work by Daniel Fisher was mostly on the random Ising more than this time. But it was the inspiration for the rules. And then there was this work by Pierre Louis-Helen to Elisa Marx. You can see that we were 20 years here. Okay? This was based essentially on this random Gaussian manifest essentially, random consideration of population. More recently, and inspired by work that has been done in the context of incorporate, this was examined by Steve Piverson, Jim Tarjur, and Larry Leif, which is Steve. And so she's scientific system. Yes,
Question,
yes.
the, here, Q is considered to be multi-composed, so in 3 dimensions, there would be 3 Qs. I mean, it's a
I
lot.
am assuming a simple growth of unidirectional. You can
Oh, unidirectional.
I assume it's unidirectional. You don't have the sum over here.
I see.
I assume it's.
Is that important?
No, it's not important. Even in 2 dimensions, for instance, in Niobium, diselenide, there are 3 over.
Right. But that's the more generic situation.
Yeah, it is, but it depends on the lattice structure. Even there, it depends on strains and those sort of things. You can actually come with the time.
But yeah, but the unidirectional.
For the purposes of this problem, that doesn't matter. It's an additional complication.
So what's the incompleteness? And if people are not sure that there is the disorder destroys.
No, the disorder is actually destroys in one major, there is no question about
Right.
it.
So what's the
point that we wanted to do, first, much of this work was out of the classical level. That's number 1. In the experiment, actually, when we look at the dynamical structure factor, you see quantum effects because you go to the very low temperature. So, when you revisit that, this is now first. The next slide. Okay, so the point is that there are new materials with high quality, both 2-dimensional and 3-dimensional, not just 2-dimensional materials these days. And the series always play a key role in their complex phase diagrams, such as in the high-TC superconductors or rare superconductors of the same ones, where they always appear in conjunction with other phases such as density waves and particular superconductivity. And so it's an important aspect of this, and this is a commercial, that these orbitals are actually intertwined in the sense that the characteristic critical points are comparable. And whenever if you think in terms of classical critical phenomena, there is no reason for that happen unless you fine-tune to some complicated. And that is not what is in actual experiment. So this is actually the problem, which is a lot of this, but I will state here. But there are new experimental techniques that have been developed that can measure the expected excitations at very low temperature. And a particular one that I'm motivated by work is this equal N-E's, this momentum resolved electron energy loss. This work pioneered by my colleague Peter Monte. So what they do there is that they have, it's a surface technique, and also we have a fluid surface, we have a solid, the test fluid well, and they shoot electrons, and they look at the electrons at Gauss out, and you can measure the energy and the momentum of the electron that comes out. And from that, by analyzing the scattering process, you can extract the essentially the spectral function of the density correlation function as a function of the momentum mechanism. So it gives you a wealth of information that never existed before. So Eels electron energy loss has been used for a long time. It was mostly a zero momentum flow. And this flow, which now is essentially resolved both in energy and momentum. They can also resolve it in spin, but most of the experiments are done without looking at spin. So this is actually important because it addresses directly the classical and quantum dynamics that we saw in a very explicit. It's complementary to other techniques which are widely used, such as outflows. These are the photo emission there, you shoot an electron, so you shoot a photon, usually an X-ray, and then what comes out is by the Roger effect, it's an electron coming out, and which measures the spectral function of the remaining photon. We can get information about the quantum dynamics of course in the materials. In particular, the high-TC materials, this is widely used. And the other one is kind of microscopy, where we can measure directly the density of states as a function of bias locally, and they can do these medical features, and you can see how the energy gaps now local influence everything. So there's a wealth of information that did not exist in 1975 when we were photographed before, that now can be addressed directly.
Right, so these new probes are, in what sense they are, um, not, are they all linear response? Should I think of them
They are
as like,
linear.
if you compute for me a density correlator,
This linear response is
all
there is a cool formula.
right? And there's a locally resolved like STM, or are they,
The STM is usually point.
right, right. No, so if the system is disordered, any of these probes can get sort of a spatial variation.
Yes, they do. We can see, for example, the variation of the IPC material. You can see how the superconducting that.
No, that's from STM and Arbus, but the new probes.
From the new probe like MEOs, they actually, you get just simply the fluctuation, the spectrum of the density fluctuations in the system.
Spatial evolution.
With the usual meals, you couldn't, but with this, actually, what you get is essentially a function of energy and momentum, but it's not like parallel.
Yeah.
It's not parallel. So it's different. So it's in that sense closer to our. Okay, RPS essentially gives you the spectral function of the whole of the electron in the material. This is the spectral function of the density. So
And neutron scattering would not, because I thought that the spectral form factor would.
spectral function
Yeah, spectral, yeah, inelastic scattering would not be
in elastic one.
neutron scattering.
Can give you that indirectly through the coupling of elements, things, but not direct.
Primarily, the interest here is 2D, right?
Yeah, this
So
is.
then getting enough signal for neutron,
Yeah,
it's
it's
stuck.
impossible.
It's,
Yeah, yeah.
it's
Yeah.
doable, but it's complicated.
So this is mostly these are surface techniques.
Okay.
MES is penetrates a little further than STM, but it's also within the skill range, so to speak. But it can be used, for example, in these twist and shout materials that I call them, because they first twist and then they shout. You know what they find? When I crack this joke, only 10% of the audience know what I'm talking about. I show my age, but they think I'm talking about classical music. So, okay, then the question is how you can, so the question, can you calculate in some model, essentially, what will be the dynamic and structure factor, essentially, including the effects of disorder? And this is a hard problem because you need to find some suitable approximate procedure. And what I do is in the theories, I call it some large number. And in fact, this is actually in a sense, Steve and collaborators, they did something like that, but they use an ON model. And I will tell you in a moment why the ON model has some limitation. You can get a closed form formula, which is, well, they do classical analysis. The quantum part is some similarities. So what I want to have is the classical model first, and we can go quantum method in some larger limit. The simple thing to do is to take, say, a sigma model, in other words, the field theory of the classical Heisenberg theory. And you can couple that, so it's more as a unit field with n components, n components, and this problem is solved over the large element. You can solve it over that as well. And here h of x is the random field. It is quenched without the random field, which was shown by Stanley a long time ago in 1968. The relation between the spherical model and this field. This is no problem. And for n greater than 2, okay, this mode is disordered, even in the absence of quench disorder. So there's no long range order at the beginning. There's long range order above 2 dimensions, but not in 2 dimensions in this case. And so in a sense, this, even though this model is like to do a number of things without directly, the problem is this has a real field. It doesn't, it's not a complex field, so I want something with a complex field that naturally will go with the physics of the simulation. Okay. Let's say, well, okay, do I know other laws that are solvable with the larger limit that involve complex fields? Yes, I do. These are under the name of CPM laws, for extension constants relating space with n components, where you replace this n field by an n component complex field, and typically you need to gauge a common U1, that's what the CPM law does. This was conducted because we gauge a subgroup that is a full array of UN in the case. And what I do here is I'm going to introduce a two component version of it. We have two such layers, one with the Z level and W, and the center. Here will be some coupling constant, and in the classical case is the inverse temperature. Okay, and there will be some coupling that relates couples Z and W, and what's going to play the role of the CDW parameter, which is complex and has a U1 symmetry that involves the mutual U1 symmetry between these two guys, is precisely the composite field Z star by W, which I wrote here, and I will identify that as it transforms under U1, and it's going to couple to impurity test.
So what's the dynamics of little a? Is it dynamical?
The little a essentially is totally unconstrained. So it's totally unconstrained. There is no, you cannot, if you want to disagree with it, there's no right. So in some senses, like the root flash from the modes of this type have shown up in theories of quantum magnetism in the form of the sugar bosons. I think it's also pretty much this predates what is just done by people in field theory in the late 70s. It's a known mode that's a little bit competitive. And in this particular case, it's actually running down.
Where is the disorder now?
There's no disorder yet. As I say, it's going to be clean. It's going to come. It's going to come. So I first want to have a clean model that I don't have to solve the human physics, the solar physics. Okay, so this approach, in some sense, can be used for other systems that have composite over parameters. And a case that actually comes to mind where we say the mathematics, where the pneumaticity is a composite over parameter. So the symmetries, they have a big symmetry group, which is a tensor product of the two U1s, the Z and W. There is a U1 subgroup they have, which is actually gauged the common U1. And the gauge field that they have in the way transforms under the station. And so the diagonal piece of U1 essentially projected out in this cut into the gauge. The place for reducing the gauge. Now the relative U1 is actually a global symmetry that remains, and that's going to be identified with the global symmetry of the whole test. Okay, so the point is that I can take the larger limit for which this U1 symmetry is still there. So first, let me solve it. So I want to solve this problem, I have to integrate the Z's and that remains. I need two Lagrange multiplier fields in terms of condition for the Z's and W's are known left. And the action is essentially based on okay, so then I do my proverbial Tauer-Slatounovich transformation for the type of this term and introduce essentially the complex field which I call sigma, which we need to sigma and star, of course. And this way, so K goes to relevant K is really nice knowledge. And so Z transforms as into the I5, W as into the minus I5, because we have it transform in opposite ways, but sigma transforms as into the 2.
Can you show the initial action?
There's two of this, which is equivariant derivative of this Z squared for Z and for W. So we see the same gauge field and both the same projection. I could have used two separate ones. And the interaction term is this.
What's the second? What's the W? Oh, okay, I was gonna ask why W.
Oh, this should have been a W, this is a misprint, otherwise they have a mistake. This should be a W.
Correct, two.
Eh?
Correct.
Or a factor of two. Yeah. Sorry over that.
So the sigma field doesn't have any constraint.
No, well, it's a sigma field is introduced as a Lagrange multiplier, well, as a decoupling field, the very old point. In a sense, it's conjugate to the other parameters, as you can see. From the view, it's like any Howard knowledge field is conjugate to the other parameters. Okay, you first take the larger limit, how you integrate out the C's and the W's. Okay, you can do that, so it's an effective action. And you can rescale the couplings G by G modulus. And then, okay, and as usual, there's a factor of this here, and this is the show allows me to start this by making some point of this. And the usual.
So that's the larger limit, like the saddle, taking the saddle points and.
Correct, because you take, so n equals infinity is the saddle point, and then whatever like the leading directions, which are important. So in the larger limit, this is essentially saturated by a solution of a lot of these equations that you will get, which are complicated, I'm sure you know. And going to look for uniform solutions with sigma naught, the two lambdas are equal to each other with maybe one center of mass, and the gauge field is equal to zero in the larger limit. Okay, so you can effectively the potential function that takes this form, and this is uneffective. Okay, now, the solid point equation essentially has a form of this type, and there is an effective of the mass capital which you need to calculate, because there is a divergence here, this lambda make this capital large, this will become singularity, so you need to go through the usual organization. So after we express things in terms of its effective of the minimum coupling, then it is covered. And then you have an effective action that has scored. Okay, now you need to look at the solutions of that. The solutions of that are the following form in two dimensions, and this and that will be local lengths. This is the feature of this, or related by line. And if it's one, is different, but then different one is. And then you get the same point equation that is. And by the sigma, you get these other equations, and more complicated. You notice is exponentials, which are characteristic of the modular dimension. So for here, you can see that this is the solution, but we need to figure an icing model, an icing model. And so you end up finding a critical value of K, Kc, which is okay. And so wait. If you live this literally, not only you have this only evaluating the memory barrier theory, because you can broke it continuously and do a single thing, which is E1 in this thing. In your two dimensions, you're not allowed to do it. Okay, but then equals infinity to the next level, and it's a critical value of K. So it's a function of K and the temperature, which is the coupling constant in the language. There is a transition from a place where rho, which is the amplitude of sigma p, is non-zero to some other place where it's different from it. Okay? So you say, well, this is the problem, this is wrong. And then you go to over 1 over n, and you find that the fluctuations of the phase field essentially having logarithmic singularity, because the fluctuations of the phases are logarithmic in two dimensions. So if you calculate the physical operators which are the sigma fields, in fact, you end up with this over here in solid regime, and there's some critical value which I identified with KT, where the vortex is essentially less okay. So in a sense, this is essentially a homogeneous fluid, if you wish. Here is essentially the plasma phase of vortices. And then you get the usual low temperature phase of the explained mode actually moves over here.
And can you be more solvable than the natural normal extract?
It's just a solve.
Just
You map it, it's like, oh, you like, the only thing the large hand theory gives you is a configuration is different. Which is all you need. Once you know what the stiffness is, you can figure out where the dimension and then the vortex operates is. And that's the argument, the energy of the argument is exactly true.
So the
That gives you this.
so the XY model happens at 1 over n level.
Appears at the other end here. So this is a peculiar, it's an example of a theory where the other parameter, actually, the amplitude is formed is at one scale, and the actual phase difference happens at a different scale. Normally, a superconductor, for instance, is very hard to say, except in the ITC, so to separate the conventional superconductor, they have to be together. Okay. So,
But isn't the different feature of the margin, like the saddle point doesn't have any interference effects, but then the interference correction.
appear to no, sure, we knew this, okay, we knew that this was going to happen, and after this was done, that's why we decided to choose it. Okay, so it has in the clean limit the correct rate differentiation, so we need to understand how it was.
So just can I just check something? So at the level of the action, all that is happening is that the grad theta squared has an extra power and
That's a coefficient of n.
yeah, so that's, you know,
So in fact, the order parameter for the initial function is a power law in this case, and the exponent alpha is actually for the one over. And in fact, the shift, the value of KKT relative to KC just shifted by 1 over. So this distance is a whole. It's a nice law. Okay, now I put the random fields if you want. Okay, so I have this n component complex fields. I can form different types of, because I have n components and they're complex, they are part of the transform under the UN group. And so I'm going to have here the generators of UN, which I denote by tau. And so I can have random field that have similarly this binomial here, which is gauge variant, by the way, essentially. There's another one, which I will take to the same, essentially having the same distribution of the same variance. The factors essentially down this together. And finally, another one with an H3, which is complex, that is going to happen precisely to this object, which, if I can do the trace of it, I will get the C. So these are my random fields, that's how they appear. They satisfy the invariant under these gauge transformations. They capture to the neuron fields, and they also capture to this neuron field. This
So when you
is,
say random fields, you just integrate out H1 H made.
okay, then I need to do the replica check. Okay. We have another n, but it's a little n, and we go to 0. Okay, excuse me. So I need to do a large n solution, so I need to do the replicator field, average of the randomness, complete traces of these towers, and you get an effective actually replica cell with the large n.
But will that be similar to, let's say, put some quadratic action for H1, H2, H3 and then integrate them?
Well, that's actually what you do, because this is what I meant to say that we have these variances is that H1 has the vanishing average and it has essentially its white lines. And the same is true with H2, and the only difference with this very complex.
So this is playing at the leading order.
Okay, this is at the leading order, you can do this. And at the leading order, what you find, again, is some transition apparently into a vortex cluster. And then if you look under the hood, you see that this dotted line over here, that's the total line, separates two regimes. One regime which I will call the weak disabled regime, and one regime called the extreme disabled regime. Because what enters here is the effective total variance, because they enter in this one quadrature.
The replica symmetric is Victorian, no?
Yeah, I take this is a replica symmetric here.
But it's not with the matrices, it's with vectors.
It's with
Yeah.
vectors. Yeah, so I don't do any replica symmetry, I stay away. As I said, I would talk for this session that was in your honor, so I need to find something
Yeah.
that was static and dirty, but I not courageous as you are, I don't go into the dynamics of the glassy state, I stay away. from it.
But let me say, up to here, everything would be doable dynamic,
Yeah,
which you may be interested or not.
Yes,
Yeah.
of course, it can be.
Relaxation, I mean.
Yeah.
Yes, I know. The quantum case is going to, I'm going to a quantum case later. Then I will have to discuss this.
So this is like, n going to infinity.
Yes, capital N, and the other end was to zero. Let's see. Okay, so the point is that there are two different regimes. In the end, there is no long-range order. These are all crossovers. You can calculate the average static structure from here, which is what you can define classically. So essentially, I go back into the rows, terms of the rows, instead of the sigma. And it's the same as the average of all average of impurities. And you find that there are two contributions, a contribution that looks like Valencia, and a contribution that looks like a double variance. Now, expressions like this have been used for ages. That have been used, they were introduced by, I think, both Grigera and collaborators, so they were looking at X-rays in the solar systems, in particular for the random field volume back in the early 80s. And heuristically, they saw that they couldn't fit things with simple Valencia, they introduced by hand and other Valencia. And there were arguments that people had pushed for, but here comes that in the Russian method. The coefficient A turns out to be basically proportional to this square to the lowest square. And since it's controlled by the strength of the disorder, and in the weak disorder regime, n equals infinity 0, this is something it's only have to work over to see it. Okay, so as I said, this type of things have been used for a long time to fit data, and recently I collaborated in the group in the while I'm working on this European ITC material MSCO, where they can actually look at the density level of the density correlation function from about 300 degrees down to essentially 15 degrees or something like that. So it's all classical. Basically, you can see the treatment time. It's a good representation. Those systems actually, because they adopt different activities, and these are the two things, two types of working, the European and the sponsoring component. What's nice about this material is that it's also density very ordered, but appears well separated from the charge density. And there's a structural transition that appears to be decoupled from the charge density. This idea to start with. The question is, can I go to the quantum case to understand the dynamics of this at zero temperature or at final?
So when you, this model intrinsically is not well suited to study diluting theories. It's really weak disorder, but yes.
Yes.
So things like domains.
It's not designed to start. I mean, I can do things like that, but it's not.
That's just a different sort of model. What I'm saying is that there are different weak disorder limits.
It's the usual question. You have strong impurities, which are few strong impurities or a lot of weak impurities.
I have a question. So related to this experiment, so experiment will be a quantum system, right? So
Yeah.
typically,
That's my coming next. Okay,
behavior will be strong.
right, because you need to go to local.
But I think delocalization type corrections in that, because that will completely change.
Okay, no, these laws that I know, as I showed you here, there is no metallic component. So I treat this as an effective theory, which is also theory, In some sense, this as if this were an insulating material. Otherwise, you got the metallic matrix, as I say, it complicates matters. Even if I ignore some instability compensation. And then contribution to the dynamics in the components when we come back and possibly in the high TC materials, you don't do that for other reasons, which is because they don't have positive particles to begin with, even though they are not. Because then that makes the very more difficult because of the strong combination. So I decided to keep it simple. So there is no metal. Thank you for the question. Should have said that from the beginning. Okay, so let me now do the solver free motion, including quantum mechanics, to say, aha, that's easy. And the next dimension, which is time, we are doing 2 + 1 dimensions, and that's usually first of all that you measure in time, and then you give the requisite analytical version to compute the real time spot. So the action is the same, except that mu on the other quantity mu takes 3 values, it's not 1 and 2, x and y, makes a function. Okay. So since you're 2 + 1 dimension, this function will be a phase transition even in the case. Okay, so the z's and w's will come in phase where they converge, it's usually the fixed phase, this bridge for the fixed phase. And then this part where the possible that appears is actually in the denominator disorder. So there's no metal. So it's really the small cell distance. So now, so first we calculate the zero temperature. So here T is temperature. Function of coupling. This is phase transition is a function of coupling constant, which is what I just mentioned. And interesting the regime that the value is greater than this critical coupling where the system is already bounded.
So how did you make it 2 + 1?
Yes.
What is what?
The big D,
Oh, big D has DT in it.
Lorentz invariant.
Yes, it's Lorentz invariant. They assume dynamical experience.
Sorry, since you got it, I wasn't going to interrupt you, but I feel like I missed something. So this is going back to my question about unidirectional charge density versus multi-directional. As we know, the unidirectional charge density wave is the spectrum. It has Goldstone modes, which are not charge density waves. They have these anisotropies.
Yes, they ignore the anisotropy in the phase. So by doing it this way, the stiffness is all the same. Whereas the two unidirectional problem,
Right.
the stiffness in only one direction is
Your complex scalar problem is more faithful to charge density.
it is more faithful, but it doesn't have the anisotropy that if you have a true Stevie value that always the phase field for the different stiffness and then the direction of the C value and the direction of the perpendicular. And then we
Not if the CDW is triangular density wave. Yeah, I guess what I'm saying is that I'm fine with this action if you're modeling phase mode of a boring, not boring, but whatever.
the boarding.
Yeah, Lorentz invariant.
Yeah, okay. So of course the two CW has all these additional contributions because the CW, this is magnetic, we have been saying for a very long time. Okay, it breaks translation symmetry and also breaks rotational symmetry, and that makes the effective action of the reciprocal.
Well, that's why I was
But
surprised.
it doesn't change the physics.
But in the weak disorder limit, you would think that the difference in the collective modes in a true smectic and to the CW, that should show up in weak disorder limit. That didn't seem to matter. Anyway, we can come back to this. You're not studying that part.
Okay. So I try to keep it as simple as possible. Okay, so one peculiarity is that this phase transition, this quantum transition, is actually fascinating. And we try to fight against it as much as we could, but there is no simple way to do it. And at finite temperature for it, returns into the three-dimensional drawing that we discussed before. Sure. And this is the this year showed me that she had found this problem in other places. And so I believe that's confronting because we seem to have the same problem. I mean, in principle, there is no reason why this transition should be further, but virtual transitions can always happen, shit happens, okay? When we need these 2-3 energies at first, we are matching the algorithms.
By the way, this is what he was planning on needing.
Yeah.
Typical. The collapse from needing the uselessness comes precisely because you always have a problem first.
Virtual transition.
So the gap is here.
Okay, in reality, as soon as you put the solver, then, okay, first of all, this is actually the n equals infinity phase diagram. This will also be affected by what I just told you about the KT transition. Except that here, probably the KT transition will also correspond, I suspect, in this level of regime as well. We also put the solver, all of these are going to be known. Also, please start with that. Unless you're like this.
So the blue dash is to be thought of as first order with a critical endpoint.
Yes, in love is a critical.
Like critical in n going to infinity and becomes critical endpoint for n fine.
Yes, well, no, this is actually going to turn into KT.
KT.
In the critical.
Okay, so then you have this, yeah.
So it means that even this is KT, there should be.
Yeah, but if you do one over n directions, then the thing of this is one over n.
This is a legal system.
But
If you do one over n, this will be shifted by what I thought. But I suspect it's hard to use a KT argument in this regime. Because in this regime, essentially, the vortices are very cheap. And then the KT assumption of the vortices. Yes.
I mean, a similar thing also exists on the conventional KT if you, the forces cheap.
Yes.
Especially
Good. There should be some technical.
On the board.
Good.
You come up with the board.
But remember that this is the vortex factor here is looked at. Because if I have a field that I have, in this case, I recently have to write some kind of strain with the using vortices, then you can kind of crystal, but in the absence of that, these are just thermal filtrations and particle for you. And they appear in the light. So there should be no difference. That's a separate question. That's like what happens in this superconductor.
Sorry, I'm got, can you go back? So, K is the parameter
Is a coupling constant
of the interaction. So when K is small, that's your ordered or positive and regular phase.
there is zero possibility. The problem is as a function, so now you have a phase transition as a function of G and as a function of K. In principle, we have temperature K and we should have G coming out of the board, which I do right here. Okay, so I showed you here that there is one regime, even for K very small, and in the absence of that, there will be some phase transition here. So this is for G less than the critical value, this is for G greater than the critical value. So there's a phase transition as a function of G.
But if I fix G and I just take K to 0, or K to be smaller,
Yes.
then what phase am I? Sorry, I'm confused because the interaction is going away.
It depends on where the coupling constant G is large compared to the critical value is small. If the phase of interest, is actually in this regime, where the coupling constant G is large enough to resolve the Z and value. Otherwise, you're always in this sort of fixed phase where the Z's and values condense. And then, of course, if the Z's condense and the values condense, they are product. That's what happens. Automatic. Similar to the Ashkin-Taylor model, we have two spins. And this is interesting phase where the spins individually don't condense, but the product does. Okay, this is another. Just because it's a composite. Okay, so let me now put the solver, and as you will see, I will not write down the replica quantum theory in Europe, but in some of the analysis. Okay, now you have quenched disorder, the same disorder we had before, but it's quenched, it's time independent. And so it's going to couple to disease and damage at all times. So the replica theory, has both infiltrations in space and in time, but the time component essentially is no longer. Okay, which is standard in possible disorder. And so you end up with this sort of bilocal interaction automatically. And therefore, when you do the larger theory solvable, now you have to use bilocal fields. Okay, so that makes the algebra a little more interesting, as you say. Interesting as in when you go to the dentist, and they tell you you're going to be somewhat uncomfortable. You know what comes. My student had to navigate through this algebra, which is not very pleasant, as some of you know. And but you can still do it. So I'm going to tell you the important results. You can calculate, you can look at the correlation functions of the propagator, which you see that way with the parameter, and calculate the self-energy, in particular the frequency dependence on the self-energy in the larger unit. I have to confess, this part of solidarity of any possibility, because the one of them is rather big, so we just need to. And there are two regimes, the weak disorder regime, the lucid propagation, and sigma, the self-energy, is under that, is proportional to the frequency square. Whereas in the strong disorder regime, even in the absence of metallic matrix, you get the self-energy that scales with the absolute value of omega, you can call it Cabrera negative. And this is clear, so it's overdone, because here is under. So let me tell you a little bit of the phase line and the phase disorder infinite views. So still a line of third transitions here, and then try to particular point. All of this will not be redundant. But what matters is now we have this additional all the parameters that come from the replica theory, essentially. So here rho is 0 and rho is not 0 in this region. In both regions here is the kappa, which essentially is essential to build the universal energy, scales by the absolute value of frequency. Whereas here it scales by the square of frequency. And that comes directly from this. So you can calculate the dynamical structure factor and also P omega, which are infinities in the larger limit, and you get a structure that looks roughly like this. Again, you still get the double Lorentzian, but that's only in the static world. It's a delta function of the frequency, which of course is natural because that's the main contribution coming from the French infinities. And then the part that has propagation is different from the strong disorder and the weak disorder. And again, this coefficient A is of order in the squares before, and in the weak disorder regime, this is another limit of the
So where is capital Q on the right hand side?
Is you don't write it here, you look at the limit of tracking things. So you don't see the problem. So in the sense, P is measured from Q. P is a small dimension. So in the strong disorder regime, you do get the sort of lumping here. In the other case, you get anything. Of course, if I were to include a metallic matrix, which is hard to do in this large approach, then you have to model with exports, but you expect to see all of that. So even this regime probably is not advantage because of the metallic matrix. But here, this is present already in the absence of a metallic matrix. This is just a coefficient that we didn't know.
Yeah, I just missed something like this. So the initial problem was that what is the mechanism of this incommensurate charge missing?
There is this rho and rest. VMware, I stay usually away from the end mechanism. So I do this in a selective. The other one, I want to know whether this is coming from the stability performance reference, which is rarely the case, but people normally are sure you. And let me discuss this later. That's the kind of worms, and assume this the logarithmic stability performance reference with sea level has never actually been
So you're putting this DBW5 through this disorder traits.
I assume that this is the value, real is the value transition, but not explain the way.
Where are you putting it in?
This in terms of this program, I feel it was this field. This is another problem. I mean, think of when you do number theory phase processing. You don't explain what phase processing becomes. You don't explain numbers. You assume there is a fluctuating number of phase. It's the same.
I don't think it does, but the gamma and the first line is not the same as the second one.
Usually it's different. These two numbers are different because they have different. Like you should have used a different signal. They have different units.
Yeah, because are related to the solvable.
They are, yes, they come. So this is related. This is present even in the clean limit. In the clean limit, you get an expression like that.
Okay.
So this is actually, so the resolver essentially gives you this effective mass. In the clean limit, which will be goes to mode, and so the mass will have to be. But here it's fine.
So how do you show me? So I think there's a qualitative, maybe an artifact of infinite end, but there's a qualitative transition from having damping to not having damping.
Right.
So whenever you see damping, the initial question would be, what's the path? Where's the path?
Well, first of all, here you don't need the bath. That's what they're
No, it's intrinsic, but like there are some modes that somehow, it's hard to know, like, yeah.
Okay.
Because if these are localized modes, then that would be an easy.
So this is what comes in the Russian, the replica limit.
Yeah, I understand. That's what I'm saying. Is there a physical?
Well, it means essentially that there is strong scattering in that limit. Okay, and in particular, because it is so very stretched, the system is not time, it's not time translation environment. Okay, so in some sense, it's surprising that there was a regime where we still actual propagation. In fact, at finite temperature, we have done some calculations at finite temperature. For instance, this actually be equivalent to infinity. So this can be done by analytical units. So at finite temperature, all these coefficients.
No, but again, at strong disorder, you have zero temperature dissipation.
Yes.
Nothing.
Yeah, right.
Zero temperature is the classical problem. It's like the two-level system, right? So always two-level system, or whatever the mechanism of the bath is.
This is usually, this is the problem if you give you static impurities. Let me finish on that this problem, which is important. Okay, so we took this simple model that is solvable, and just like it. This way there is, I can get results out of it. It's consistent in the sense that this is the correct classical limit. So you can find the pure system, and you can study effects of this level in this larger level. Which exhibits this crossover between underground and so the process is more evolution. So let me address the question. So let me try go to the problem calculation of the conductivity in the dirty metal. And you take static impurities. Okay, and you calculate longitudinal sensitivity. Then you can ask where the dissipation was. And it's exactly the same thing. So it comes because essentially you have a reference system and your pinching is essentially the singularity is pinching the branch test. Okay, so the system is acting as if it were open. And that you are open to the internal way. from my memory. If here is something that's nice to say. This is, why do I get, how do I calculate it? If you want to do Boston connectivity, just by summing the way of scattering, instead of static scatterings in metal. How you get there?
No, I'm not sure I understand the analogy, because in dirty metal, you basically say you have a finite density of states with fermions
Yeah.
that remains finite to zero temperature.
Yeah.
I think that, if I understand correctly, the interesting or the surprise about the original two-level system, sort of a phenomenology of Barman, whatever it was, that there are these two-level systems, God knows where they come from, but they never freeze out if they go to low temperatures. Right, so I kind of feel like you have a
Here,
classical
the
photonic
result actually is traveling on the modes.
So these modes remain active to zero temperature.
That's because of this order is curving.
You just generated a finite density of states.
It's not a system that can have a clean up.
Yeah, okay.
It's made in sense.
It has to have a finite, I feel like bosonic oscillator modes with finite density of states. Nice.
Okay, the disorder essentially is filling up the gaps.
So that's really technicality. From the replica point of view, you do have a transition between uncoupled replicas to coupled in the replicas. You do have a transition. So this would reflect in, in the dynamic of the machine, which could mean that the system doesn't equilibrate immediately. Yeah. Would it be interesting at all to know how these orders spread?
I'm not sure if any of this is done with medicine. They don't even see, you should see, when you go to therapy, because you're familiar with the way the system. Only baby there's a sample, should be like this, and cannot see. Because only there are some of them, new approaches, really confident approaches. We have to be like that, approaches where they say the vector at the same time, because in microwave, it's happening, it's literally dry, the system is open. And then the kernels move.
Those are out of the
Those are all out of the.
Well, I know, but there is an equilibrium cousin of that. This is something that's arbitrage. Other people have been doing is if you think of optics, the usual, and we use, well, with leading word on it. Basically, the idea is that the usual thing is that if you shoot omega, out comes out omega, that's your linear response. But if there are two omegas, if you look for the next order, the thing that depends on omega 1, omega 2, it's like to these NMR spectroscopy or anything, there's lots of these two frequency kind of probes. And the idea is that somehow it's like you create an excitation and then you do a linear response of that.
But the only thing in those experiments they can see is theoretic.
No, but, right, so what I was gonna say is that, for example, your model omega thing, there's a path of oscillators, and linear response, you cannot tell if those things are localized or not. So, but for example, if they're just like localized to level systems, then if you could ask about, you could see joule heating of these things, you could see that you could easily, so if you have, two level systems, their two frequency response has a 1 over omega 1 minus omega 2, and a singularity that, like, if you actually pump them, probe them, there's perfect history, there's perfect memory. You change their distribution.
So in some of the systems people got done from experiments.
I think pump probe is like far from equilibrium, but I think
Those
stuff
are,
that,
usually, but typically what we see is diffusion. They pump the systems, you go to a 3 electron layer, so it's time. So they pump the system and then they measure the X-rays essentially to this point. And they see the relaxation of equilibrium, and that you can typically fit that in some way at the middle of the day.
But yeah, but I think the more precision.
But those experiments are usually relatively high temperatures, and it's really hard to work with low temperatures because of the fact.
It's just sort of a multi-dimensional spectroscopy angle that's. That's more precision kind of.
I know, the other one is more brutal.
And in fact,
I agree.
but that would be sort of a multi-point correlator of this, because so
For
far.
this, I will have to go to the four-point function.
Right.
And I tried to tell my experimental collaborator had to measure the four-point function to right out.
Will not be happy.
Well, but an optic would be in their fashion.
Yeah.
Their fashion.
It's very hard to do, actually. For instance, in Newton's pattern, for instance, they have been trying to work for a very long time. You see, for instance, given a field matter, you need to calculate and develop it. Before paper. No one to say about it.
But I thought using all of these things will show up in optics. So there is already an established sort of literature on that. By establishing class, right?
That is not to say that the theory is that those are easy to understand.
And somebody else.
Those calculations are often highly unreliable. Okay, here at least I have a no, which is larger.
No, but you were saying that the experimentalists, your experimentalists don't like to do this to higher order, but like the
They don't.
opticians
I mean,
can. Okay, anyway. All right, let's thank you. Are there any questions online? Sorry. Okay, otherwise, thanks for tuning in.
The company you had